The topic of uh, presentation is switch mode converters for utility interface. That in that one, by using the converter, we can control the power flow between DC source or a battery and an AC grid. And if the power flow is from a DC source into the AC grid, then converter is working as an inverter. Now, if the power flow is from the AC grid into the battery or DC source, then converter is working as a rectifier. For all the concept will be explaining in the coming slides. Switch mode converter for utility interface. Therefore, this diagram represents the single phase H bridge converter, and these are the 4 switches, and there are 2 legs, and across each switch there are feedback diodes are there, and this is a DC source at this side, and on this side there is an AC single phase AC supply VS, and the output of the converter, that is represented as V converter, and there's a linking inductor that is connected between the AC source and this converter output or the converter, and that is the LS, that is the inductor, and here the corresponding current from the source, that is IS, is the current from the source, that is marked as in this direction. If it is considered in this, we'll be considering as a positive. Therefore, if the power is flowing from the AC grid into the DC, then what we are getting is a positive current or positive power flow. And if it is reverse case, in that case, this will be working as a rectifier. Now, if the power flow is from the DC source into the AC grid, then the direction of the current will be reversed, and then this converter will be working as a inverter. Therefore, now coming to that one, the IS, that is the current flowing from the AC source into this converter input or V converter, and here IS1 is the fundamental source current, that is IS1 is the fundamental source current, because this IS involves fundamental plus harmonics, because the V converter one voltage is fundamental is the, then harmonics also there. Therefore, the corresponding current IS, that involves the fundamental current plus harmonics. Therefore, IS1 represents the fundamental source current, and the VL1 is the drop due to IS1, that is the drop due to the fundamental source current, that is the drop across the inductor, that is represented as VL1, the voltage across the inductor due to the fundamental current IS1. Assuming Vs to be sinusoidal, what we are assuming is that the input grid source is a purely sinusoidal one, and the fundamental frequency component of this one, V converter, that is V converter 1, that is the fundamental V converter 1, fundamental component is V of the V converter is V converter 1, and the fundamental component of IS equal to IS1 of the frequency, and of the fundamental frequency component V converter and IS can be expressed as V converter 1 as well as IS1 respectively. Then if you draw the phasor diagram here, you can see that one, this is the voltage at this one, that is the voltage grid side voltage, that is the voltage Vs. Actually, this voltage, if you apply the Kirchhoff's voltage law in this loop, and if you draw the corresponding phasor diagram here, this Vs is the vectorial sum of the converter 1 voltage as well as the drop across the inductor due to the fundamental current IS1. Therefore, it is V converter 1, that is V converter 1 is vectorially added with the drop across the inductor due to the fundamental current VL1, and that gives the total voltage Vs. Therefore, the Vs is the vectorial sum of, or the phasor sum of, the V converter 1 and VL1. Or the current through the inductor will always be perpendicular to the drop across the inductor. Therefore, the IS1 will be perpendicular to the VL1. Therefore, here VL1 we are extended and perpendicular to that one. This is of 90-degree angle, or that is, this is the current, fundamental current flowing from the AC source, that is IS1. This is the vector IS1. Therefore, and this angle is defined as angle OAC. That is why this is equal to 90 degree. OAC, this angle equal to 90 degree, and the corresponding angle COA, that is COA, that angle we are finding as that a phasor angle between the fundamental or the AC voltage Vs as well as the fundamental current IS1. That angle is represented as theta. So for this 90 and this angle is theta, from this triangle it is equal to 90 minus theta. That is angle ACO, that is equal to 90 minus theta. Therefore, this is the in this case the voltage across the inductor due to the fundamental current, which is equal to Vs equal to j omega Ls Is1, or Ls equal to dis1 divided by dt, and the drop across inductor across equal to j omega Ls into Is1. Now continuing the phasor diagram of switch mode converters for the real and reactive power control as such here. This already I explained here. This is the phasor diagram of this loop as such. Here this Vs equal to the vectorial sum of the converter 1. That is fundamental component of the converter voltage V converter 1 as well as the drop across the inductor due to the fundamental current or VL1. That is the total Vs, and already we explained. Now the real power, that is the real power flow from the this one AC grid into this DC side, or the real power flow can be calculated at P equal to the voltage, this voltage Vs into the fundamental current Is1 into the cosine of the angle between this one, that is cosine of angle between Vs and Is1, which is equal to cos theta. For this is the real power, or here Vs into this Is1. Is1 is the drop across the inductor due to this, sorry, it is the drop across the inductor VL1, that divided by the reactance. Therefore, Is1 is replaced by VL1 divided by the reactance equal to omega into Ls into, of course, the cos theta. Or here again coming to this, we have to replace the VL1 cos theta. For that one, we have to consider this triangle. Triangle OBC is considered. OBC triangle is considered. Now in that case, BC by, that is BC by sine delta, as per the trigonometric rule here, BC divided by sine delta, that is equal to OP, that is OB divided by sine of this angle. Sine of this angle means sine 90 minus theta. Sine 90 minus theta. Or this B, that is we can say that BC equal to, it is equal to VL1. VL1 divided by sine delta equal to OP, that is OB, which is equal to V converter 1. V converter 1 divided by sine 90 minus theta, or that's equal to cos theta, or V converter 1 divided by cos theta. Therefore, VL1 cos theta equal to V converter 1 sine delta. Therefore, we are replacing VL1 cos theta by V converter 1 sine delta. Therefore, it is equal to, we can VL1 cos theta equal to V converter 1 sine delta, that is substituted, and that is reduced, that P equal, we are multiplying Vs in the numerator and denominator, so that the final equation for the real power flow, which is equal to V square divided by omega Ls into V converter 1 divided by Vs. We are multiplying Vs and Vs here, but that's why it is came V square. V square divided by omega Ls into V converter 1 divided by Vs into sine delta. Therefore, this sine delta. Therefore, this is the real power flow between the AC grid and the DC source. That means that the real power flow P is a function of converter 1 as well as delta of cosine delta. Therefore, by controlling this delta, that is this angle, that is the phase angle of between the Vs and V converter 1 and the magnitude of the V converter 1, we can control the real power flow between the AC grid and DC source. That is regarding the real power flow P. Now continuing the phasor diagram of switch mode converters. Switch mode converter, same diagram is shown here, and this is the same vector diagram is, or phasor diagram is shown here, and the real and reactive power control. In this slide, we will be explaining what is the reactive power flow between this AC grid and DC source. Reactive power equation basic Q equal to, that is grid voltage Vs, that is AC voltage Vs into the fundamental current Is1 into sine of angle between that one, that is this angle sine theta. For this is the reactive power flow between the AC grid and DC source. Therefore, here we can say that Q equal to Vs. Again here this IS1 is this one IS1, that is this current, the fundamental current through the inductor, that is equal to the drop across the inductor due to the one, that is VL1 divided by omega Ls. Therefore, IS1 is, we are replacing the IS1 by VL1 divided by omega Ls. Therefore, Vs into VL1 divided by omega Ls into sine theta. Now here, now let us see that one. We are considering this triangle. We are considering this, this triangle BCD. We are considering this triangle BCD. In that case, angle here BCD, this angle equal to 90 minus theta. Already we have seen this angle equal to 90 minus theta. Or here we can say that one VL1, if you take this one CD cos 90 minus theta equal to VL1 divided by, CD divided by VL1, or CD equal to this distance, this CD equal to VL1 cos 90 minus theta, or VL1 cos 90 minus theta equal to CD. Therefore, here, first thing is that we have to find out here VL1 sin theta divided by omega Ls, or VL1 sin theta equal to, that I can write it as VL1 cos 90 minus theta, because sin theta equal to 90 minus theta. Therefore, I am replacing VL1 sin theta by VL1 cos 90 minus theta. Now, VL1 cos 90 minus theta, as I explained, VL1 cos 90 minus theta is nothing but this vector CD. Therefore, that is equal to vector CD. Or CD, I can write it as, it is the difference of OC minus OD and OD. Or OC minus OD equal to CD. OC minus OD equal to CD. OC is nothing but it is equal to the grid voltage Vs. Therefore, the Vs minus, what is this one? What is OD? OD is V converter 1 cos delta, or cos delta equal to V converter 1, this one divided by cos V converter, or this is equal to V, here this one equal to V converter 1 cos delta, or here V converter 1 cos delta. That is why here we are replacing that one, that is VL1 cos theta, or CD I can write it as the vectorial difference of Vs minus V converter 1 cos delta, minus V converter 1 cos delta is nothing but OD. Therefore, this is the VL1 sin theta. Therefore, I am replacing this VL1 sin theta by Vs minus V converter 1 cos delta, or substituting that one, Q equal to Vs divided by omega Ls into Vs minus V converter 1 cos delta, or the reactive powers equal to Q equal to, supplied by the source equal to Vs square divided by omega Ls into 1 minus V converter 1 divided by Vs into cos delta. Therefore, this is the equation for the reactive power flow. We are multiplying here Vs numerator and denominator. That is why we are getting equation like this one. Therefore, this is the reactive power flow between the grid and AC source and the DC source. And previously we have calculated what is the real power flow between the AC or AC source and DC grid as well as DC source. In terms of the, what we have to control is basically we have to control the magnitude of the converter 1 voltage and the phase angle of the V converter voltage with respect to the grid voltage. That is, delta is to be controlled. Similarly, the magnitude of V converter is controlled, so that we can control this. Because if you see the locus of this one, if you see the locus of the V converter 1, it is just like a circle. It is in the form, it's changing as a circle. Similarly, based on that one, VL1 is changing. The phase of VL1 will be changing. Always you know that the current through the inductor is perpendicular to 90 degree, or that is 90 degree with respect to the VL1. That is why as this is rotating, as V converter 1 is rotating through a circle fashion, the VL1 is also rotating, or that automatically rotates the vector or IS1. The fundamental component of the source current is changing like in a circle fashion. Therefore, coming to that one, basically by controlling the magnitude of the converter 1 voltage, that is this converter 1 volt, fundamental voltage of the converter, that is called, as well as the phase angle of this converter 1 voltage with respect to the grid voltage Vs, we can control the real and reactive power flow between the AC grid and DC source. That is the basic concept. Now continuing the rectifier and inverter mode of operation of the switch mode converter, as we have seen already, then the real power flow is equal to P equal to Vs into Is1 into cos theta. And we have already derived that, the equation for the real power flow between the AC grid and the DC source. And in that case, if you make the converter 1, if this is corresponding to the rectifier mode of operation, so that if you make the converter 1 volt with like this much magnitude and this phase angle here, of course the VL1 actually the converter 1 voltage plus VL1 equal to the grid voltage Vs. So this is the VL1. Always, as I already explained that one, the current through the inductor is 90 degree. Of course, that is lagging the voltage. Therefore, this is the current through the inductor Is1. The fundamental current through the from the source, that is Is1 vector is this one, and this is the VL1. Or meaning that if you make the V converter 1 phase magnitude of this much and with a phase angle delta lagging the Vs by phase angle delta, then automatically the Is1 will become in phase to Vs, meaning that the fundamental current from the source that will be in phase to the source voltage or AC voltage Vs, meaning that the power is flowing from the AC side into the DC side, or this is working as a rectifier. Therefore, that is the phasor diagram corresponding to the rectifier mode of operation. Now, if you adjust the converter voltage, this converter fundamental voltage, this is the second case. Converter 1 fundamental voltage is made to lead the Vs1. Second case here. You can see that one. Then, in order to get this vectorial sum of V converter 1 plus VL1, that is the total voltage, the supply Vs input voltage, AC voltage. Here we can say that this is the inductor voltage, and to that one the current will be perpendicular to that one. Therefore, in that case the current vector will be 180 degree out of phase. Therefore, here the current through this one is 180 degree out of phase with the this grid voltage, or the current will be flowing from the DC side into the AC side, or the converter is working as an inverter. The power flow is from the DC side to the AC grid, so this converter is working as a inverter. Therefore, in this case, by making or by controlling the converter 1 to have a magnitude of this one and leading the Vs by an angle delta, we can make VL1 like this one, and automatically, as I already explained, the current vector will be 90 degree lagging with respect to this voltage. Therefore, automatically the current through fundamental current through the inductor becomes in this one, meaning that Is1 will be, the phase angle with respect to Vs is equal to 180 degree. The phase angle of Is with respect to this one equal to 180 degree, or the power flow is the reverse direction from the DC source into the AC grid, or the converter will be working as an inverter. Therefore, that is the phasor diagram corresponding to the inverter mode of operation. Therefore, basically we are controlling the magnitude of the fundamental converter voltage as well as the phase angle. Thereby, you can control the converter either power flow from the AC grid into the DC source, then converter is working as a rectifier, or the power flow from the DC source into the AC grid, then the converter is working as an inverter. That is indicated in the phasor diagram. Therefore, continuing the bidirectional power flow, what I already explained in the previous slide here, the reactive power mode of operation as well as, rectifier mode of operation as well as inverter mode of operation. In rectifier mode of operation, we have to make the converter 1 voltage phasor be lagging the Vs by a certain angle delta, so that VL1 will be basically what we are controlling is by controlling V converter 1, finally we are controlling what is the vector voltage across the linking inductor. Always once it is fixed here, the current will be always perpendicular to VL1. Therefore, this is the phasor diagram corresponding to the power flow from the grid into the DC source, or the converter is working as a rectifier mode of operation, as I already explained. And this is the phasor diagram corresponding to the inverter mode of operation, in which this current, that is current is flowing from the DC side into the AC, or this converter is working as a inverter. And here also what to be done is that the fundamental component of the converter, V converter 1, the magnitude is adjusted. Similarly, the phase angle of this converter 1 with respect to the grid voltage. Here you can see that one compared to this one, this is leading this one. So that this will be the voltage across the inductor. Once the voltage across the inductor is this one, the current will be perpendicular to, since it is an inductor, the current through the linking inductor will be perpendicular to or lagging 90 degree with respect to VL1. So IS1 will be perpendicular. Or we can see that one, the phase angle between VS and IS1 is 180 degree, meaning that this power flow is the reverse direction. In that case, the delta S is equal to negative, mean we'll be getting a negative power, or the power is flowing from the DC side into the AC grid, or the converter is working as an inverter. That is already I explained that in the previous slide. Therefore, this is the inverter mode of operation and this is the rectifier mode of operation. What we are doing is we are controlling the fundamental component of the converter, both magnitude and phase angle. Thereby, you can change the power flow from DC between the DC source, between the AC grid and the DC source. Therefore, by controlling the magnitude of the fundamental converter voltage, V converter 1, and its phase angle with respect to the source voltage, that is delta, bidirectional power flow between the DC source and AC grid can be controlled. That is, the bidirectional power flow between AC source and DC source, either it can be in this direction, then it's working as a rectifier, or if in this direction, it is working as an inverter. Basically, what we are doing is we are controlling the fundamental component of the converter 1, magnitude as well as phase angle. That is, here the magnitude as well as the phase angle with respect to the source voltage. This is lagging the source voltage by an angle delta. Then it is working as in rectifier mode of operation. In this case, we can see that V converter is leading the VS by an angle delta, and this is VL1. And in this case, it is working as an inverter, or the power flow is in the reverse direction. That is, here P will become negative since delta is negative, and the power is flowing from the DC side into the AC grid. Then the converter is working as an inverter. Therefore, that is the way how the power flow can be controlled between the AC grid and DC source. Now in this slide, I'll be explaining how you can control the fundamental component magnitude as well as phase angle with respect to the grid voltage. That is using a PWM bipolar switching method. I'm explaining. This is a full bridge converter, but we've already seen. These are the 4 switches and these are the feedback diodes. And this is the DC side and this is the AC side, as such this one. In this case, the switching algorithm of the PWM switching algorithm here, what we are taking it as that there are 2 signals are there. That is, high frequency triangular signal is compared with a low frequency sinusoidal signal, or this is called the reference signal, or sometimes we call it a modulating signal, and that is compared with a high frequency triangular signal, that is a switching signal. And there are 2 terms to be explained, or that is called modulation index. Modulation index is that maximum, see that modulation amplitude modulation index means maximum magnitude of this control signal, that is maximum magnitude of this modulating signal, maximum magnitude divided by the maximum magnitude of the triangular signal. That ratio we call it as amplitude modulation, MA. And why I'm telling you that one, as we are, if the logic to switch here, that one, if once the magnitude of the modulating signal is more than the triangular signal, that is, if it is in this case, then these 2 switches are made to on. And if the modulating signal is less than the triangular signal, these switches are on. Therefore, once the modulating signal is more than the triangular signal, these 2 switches are on, meaning that here we'll be getting a voltage plus VD. That is, that the plus VD will be getting. And once the modulating signal magnitude is less than, or the triangular signal is more than the modulating signal, these 2 switches are on. Or in that case, we here will be getting it is equal to minus this voltage VD here, minus VD. Therefore, we can see based on that is the switching algorithm used, that is given the control method of this one, switches are given as per this equation, and we'll be getting either plus VD or minus VD depending upon the relative magnitude of the modulating signal and the triangular signal. Therefore, this is a sine modulated output here. And if we do the Fourier analysis of this sine modulated output signal, that contains the fundamental plus harmonics. The harmonic will be centered at MF, 2MF, where MF is the frequency modulation index. Therefore, here, what the fundamental output voltage, that will be in phase to the modulating signal. The fundamental output voltage of this inverter output, that will be in phase to the modulating signal. Another one, the magnitude of fundamental voltage is given by MA into VD, where MA equal to, as I told you, it is the ratio of the modulating signal, amplitude of modulating signal to the amplitude of the triangular signal. Therefore, as we control this ratio, or normally the magnitude of triangle signal will be kept constant and will be changing the amplitude of the modulating signal or reference signal. By changing this one, we can change what is the MA, or thereby you can change the magnitude of the fundamental voltage. That is, this is the fundamental voltage. As we have seen V converter 1, no, in our previous slide, V converter 1. That means that, of course, that the fundamental magnitude of this voltage, converter voltage. The fundamental magnitude of that is the maximum magnitude of this one, that is given by MA into VD. Of course, RMS value equal to MA into VD divided by root 2. Therefore, by controlling the modulation index, MA, amplitude modulation index, we can vary the magnitude of the fundamental voltage, or we can say that this voltage, this voltage magnitude can be changed by changing the modulation index. Another one, the phase angle between the V converter and delta. Of course, I told you, the phase angle of the fundamental is same as the phase angle of the reference or modulating signal. Now, if you change the phase angle of the modulating signal with respect to the grid voltage, then we can change the fundamental output voltage angle with respect to the grid voltage. Therefore, since the fundamental output voltage of the inverter or PWM inverter is same, or that phase is same as the phase of the modulating signal or reference signal, by changing the phase angle of the reference signal with respect to the grid voltage, you can vary the fundamental converter output voltage phasor with respect to the grid voltage. Delta can be changed. Therefore, by these two means of that one, by controlling the modulation index, we can change the magnitude of the converter 1 voltage. And by changing the phasor angle of this modulating signal with respect to the grid, we can change the delta. Thereby, you can have a power flow control. If you make a delta like this one, the power will be flowing from the DC side. This is working as a rectifier from the AC side into the DC side. So that is working in a rectifier mode of operation. And if you make the delta angle, which is V converter 1 voltage is leading this VS by an angle delta, then the power flow will the reverse direction, that is from DC to AC, or that is working as an inverter. Basically, we are controlling the magnitude of the fundamental V converter 1 voltage by controlling the modulation index. In a PWM, modulation index controls the magnitude of the fundamental, and the phase angle of that one can be controlled by controlling the phase angle of the modulating or reference signal with respect to the grid voltage. Therefore, that is the way how we can control the power flow between the DC source and AC grid using pulse width modulation technique. This is a bipolar switching method, and this is a switching algorithm that we are following, and this is the corresponding phasor diagram which I already explained.